Welcome to Lesson 3, Graph and Compare Savings Growth. Our objectives are to take our equations that we use to calculate future value, and we will graph those. So some of those are exponential, and then we also have the simple interest, which is a linear function. So we're going to be graphing both exponential and linear functions, and then we're going to analyze and compare the growth between these functions. Down below here, I have a couple of graphs. This first one on the left compares the way compound interest grows as compared to simple interest, and you can see that the amount under compound interest grows exponentially. It starts off fairly slow and then immediately starts to curve up faster and faster. Whereas if you have an account that just earns simple interest, your account increases by the same amount over time. This graph over here compares compounding interest, but with two different rates. In blue, we have 8% or 5%, and in red we have 8%. And you can see that after 20 years, there's quite a bit of difference in the future value of the account when you earn 8% compared to 5%. It can make a very big difference at the end. Not so much in the first 5 years, but definitely over 20 years. Let's go ahead and review our three main equations. So we have simple interest, compound interest, and then continually compounding interest. Our first one here is simple interest. And remember that in this equation, what's different than the other two is that in this equation, we end up finding the interest amount, not the future value. To find the future value, you have to take the interest and add it back to your original principal. So again, this is interest equals principal times rate times time, and we will add this back to our principal. Our second equation that we have is for compounding interest. So our future value in here is equal to the principal times our rate, basically, 100% plus our rate, raised to however many periods we have. And then our final formula, remember, is for continuous compounding interest. And we use this E, which is 2.718. It's just a number. So our final value, or our future value, is equal to our principal, or our present value, times E raised to the rate times time. And remember that we have to do E raised to the RT before we can multiply it by P. Looking at these graphs, when we have a simple interest graph, remember that it follows this straight line. So in reality, this is our y equals mx plus b. And this line right here is just y equals mx because we started our origin with 0. But as soon as we invest something, we would have a plus b, showing that we would be investing say $50 or $100, we would actually, our graph would then shift up if we invested $50 here, and our line would go up from there. And then this equation would actually be y equals mx plus b. Okay, moving on, let's look at the graph of a compound interest account or continuous. They're going to be really virtually one and the same. This follows the exponential growth graph, which is y equals a times b raised to, and so b is our base, which would represent this e, and then the RT represents our x, the rate times the time. In all of these equations, x is going to represent our time. So let's go back and actually create some of these equations given a real-life scenario. In our first example, we're going to invest $100 at 10% simple interest for 10 years. And remember that this is our account, or our formula. So when we write out this and make it fit into this, we want to keep in mind that we're trying to follow y equals mx plus b. And that is our linear equation written in y equals mx plus b, or slope-intercept form. So we don't know the future value amount, we'll call that y. But we do know that our present value, or our principal, is $100, and our rate is 10%. Our time is x, and then we want to know the future value, so we would need to add that $100 back in at the end. So this amount here is going to get us our interest, and this amount here on the end is our original principal that we would add back to the interest to find our future value. So really, this p here, we would need to say plus p on the end. So let's simplify this so that we can graph it. We would have y equals 100 times 0.10 is going to be 10x plus 100. So this is the equation we would graph, which is very simple to graph. You can see the y-intercept is 100 and our slope is 10, or 10 over 1. Now let's go ahead and look at this second equation. In this one, we invest $100 at 10%, compounded annual interest for 10 years. And I use the annual interest just because it's a little bit simpler than n is 1 and n is 1 here. But we could definitely put in monthly and make this be 12 and this be 12 as well. Okay, so we are really trying to mirror this equation. If you remember, y equals a b to the x. And this is our exponential growth equation. So if we start off and fill in what we know, our future value is going to be our principal, which is $100, times 1 plus our rate, which is 10%. Remember that this is just over 1. And then raised to the nt. Well, n is 1, and I'll go ahead and write that in. And our time period is going to be x. We know here that we want to invest for 10 years, but we're going to put x because we want to see what the growth is each year over 10 years. So simplifying it so that it looks more like y equals ab to the x, we can get y equals, and then we're going to have 100, and then here 1 plus 0.10 is 1.10 raised to the x. So a represents our starting amount, the 100, 1.1 represents our growth, and then x represents our time. So now we can graph this equation fairly easily. This is just an exponential growth equation. Okay, on to our last problem here. We're going to invest that same $100 at 10%, but now we're going to compound it continuously over 10 years. Again, we are trying to use the y equals ab to the x. So we have y is equal to 100. And then let's go ahead and fill in a number for e. The 2.718 is our number, raised to our rate, which is 0.10, 10%, times x. And now we've already written this in this y equals ab to the x form. So this is the equation that we will graph when we are graphing continuously compounding interest. So we have our three equations, which looks very familiar with things that we already know how to graph. Let's go ahead and graph. Here's our first one, y equals 10x plus 100. If we're going to graph this, we would have our y-intercept at 100, and then our slope is just up 10 over 1, up 10 over 1. So let's do this. When we'll have an x and a y. When x is 0, we know that our y-intercept is 100. And I don't want to take time to plot all these dots, so I'm just going to figure out what is y after 10 years. When x is 10, 10 times 10 is 100, plus 100, I get 200. It's a lot easier to take and plot 2 points and connect them with a line. And there is our simple interest graph. And true to form, it is linear. It grows at an even amount each period. Okay, so let's keep that on the graph, and then let's look at graphing our compounding interest. So here was our equation, 100 times 1.1 to the x. So if we go ahead and do the same thing that we did before, and this time what I'm going to do is put in a couple more than just 2 points. I don't want to just do 0 and 10 because I know since this is raised to the x power, this is going to be an exponential graph. So it's going to curve up. So I want to make sure that I capture the curve a little bit better. So I'm going to use 0, 6, and 10. Well, anything raised to 0 power is just 1. So 1.1 to the 0 power is 1, and 1 times 100 is 1 as well. So here's my x, here's my y. Now let's go ahead and use 6. So let's take 1.1 raised to the 6th power, and then let's take that multiplied by 100. So we should get 177 with a little bit more. So I'm just going to round to 100 and 77. Finally, let's do 10. So let's take 1.1 and raise it to the 10th power. We get 2.59. Multiplying that by 100, we get 259 and a little bit more. So I'm going to round to 259. Now I can plot these points. 6 and 177 is going to be very close to the 180, so that's going to be up here. And then 10 and 259 is going to be almost 260, so that's going to be way up here. And then of course my initial number, notice, is still that 100. So the tricky part then is drawing the curve for this, making it look somewhat straight. And that's, easier said than done. So it's going to look something like that. And notice that we have a curve. It's not a straight line. Make it a little nicer here. And it goes up. And this is our compounding annually. So this is compound annually. And you can see that around 10 years, we start to grow, and that's where the exponential curve starts to come into play. Okay, let's look at our last example. Remember, our last example was if it was continuous compounding, so it compounded continuously. Well, once again, let's go ahead and use 0, and then let's pick a couple of strategic points. So let's pick our 6 and 10 again. Well, -1 times 0 is going to be 0, or I should say 0.1 times 0 is 0. Anything raised to the 0 power is just 1. So we end up with 100 times 1, which is again 100. So there's our first point, which makes sense. We started with 100. Now let's go ahead and figure out 6. So we'll need our calculator for that. So the first thing is we need to do our exponents. So we take 0.1 times 6. That gets us 0.6. Now we need to take 2.718 to the 0.6 power. I happen to have an E button here, so instead of typing that in, I'm just going to hit E, raised to the 0.6 power, and that equals 1.82 multiplied by 100, and that equals 182. All right, let's do one more so we can get the full effect of the curve. Let's do the 10. So now we have 0.1 times 10, which we know is going to be 1. And then we have E raised to the 1 power, which you know is just going to be E. And then we multiply that by 100, which will be approximately 272. Now I'm ready to plot these points in graph. So at the 6, I'm up here, and these go by 25s, 25, 50, 75, 100. So I'm going to be somewhere up here. And then at the 10, I'm going to be up at 272, so it's going to be right around here. So again, the tricky part is, how can I make a nice curve? Sometimes I do dotted lines, and then just try to connect those. So there we have our compounding continuously. And you might ask yourself, wow, that's not that much of a change from our compounded annually, which is the red line here. But remember that compounded continuously ends up just coming to this 2.718 base, and we demonstrated why that worked. We derived that in a previous video. So there really isn't a lot of difference as you start to compound monthly, or daily for that matter, as compared to compounding continuously. Okay, let's look at our last example here where we analyze some of this. So what I've done is I've graphed these nicely on a computer so you can see how they actually look. And this last example was when we did our continuous compounding, but remember that we have our simple interest here. We have our annual compound interest in this red color, so this is annual. And then we have our continuous interest in blue up here. So this one is continuous. So if we are going to analyze, obviously we can see that continuous interest is going to give us the most amount of earnings. And let's actually draw a line here at 10 years. because our goal was to invest this for 10 years. So you can see here, if we make some points, simple interest only gives us about $200. Compounding annually gives us about $25, $50, maybe $255, something like that. And then compounding continuously, and we have those answers, was, forgot what that was, about 278 or something like that, and that's a little bit higher. And we did calculate those already. So we can look at this graph and we can see easily that compounding continuously is our best bet, but compounding at all still works very well. Now let's actually take what we made. Let's go back and figure out what those amounts really were. So 272 and 259. So this is 259. This is 272. And then simple interest was here at 200. We can analyze and say, how much interest do we earn? Well, we started with 100. So if we started with 100, that means we would earn $100 of interest in 10 years if we compounded using simple interest. We would earn $159 after 10 years if we compounded using annual compounding, and we would earn $172 if we had continuous interest over the 10 years. And that concludes our lesson today on graphing and comparing the savings growth between exponential and linear functions.